Funciona, não?
Hello, everybody. Let's start with this afternoon session. It's my pleasure to introduce my good friend, Otoniel Nogueira da Silva. He did his PhD thesis here at ICMC, and then he spent 3 years with us in Cuernavaca, in Mexico. Afterwards, he preferred to come back to Brazil. He stayed first here at Universidad Federal de São Carlos for a while, and now he is professor at Universidad Federal de Paraíba in João Pessoa. He works on problems related to equisingularity, mainly for spaces and maps, for curved surfaces, and also some higher dimensions. And today he's going to talk on invariance of quasi-homogeneous map germs.
So, thank you very much, Jawad, for the introduction. So first of all, I would like to thank the organizers for the invitation. I'm very happy to stay here. São Carlos is a house for me. And Cuernavaca, it's also a second house for me. And I'm very happy to stay in this important meeting. Okay, today I would like to say some words about invariance of a quasi-homogeneous finitely determinate map germ from C2 to C3. Yesterday, we had a very nice talk about maps given by Roberto Jimenez Conejero. It was a very nice talk. And today, I would like to say some words about the case of C2 to C3. Okay. It's convenient to make a very quickly review of the notion of finitely determinate map germs, especially in the case of C2 to C3. So what is the meaning of finitely determinate map germs? The second important element in my introduction is what kind of invariants I would like to consider in this talk. They are analytical, are they topological? And the third thing in my introduction is what is the motivation to consider the quasi-homogeneous case? Okay. Just a spoiler for the motivation. I will consider two problems in this talk. The first problem is about the J invariant of a map germ introduced by Noia Ballesteros and Tom Manar. The second problem is about the transversal slice of a Kronecker map germ. Okay, the topological type of the transversal slice. Okay, just a spoiler. What is a finitely determinate map germ? Of course, everyone knows something about this. I will make here just a review of the notion. A first remark is this notion is equivalent to other notions like a finite map germ or map germ with isolated instability. But I will avoid these definitions, and I would like a more geometric characterization of this notion. So in this sense, you can use Matter-Gaffrin result, a Matter-Gaffrin criterion, to give a characterization of finitely determinate map germ. Okay, so Matter-Gaffrin criterion, in this case, says that F is finitely determinate if and only if there is a representative, here U is a neighborhood of 0 in C2, and V is a neighborhood of 0 in C3. Here in C2, here in C3. So that when you consider the pre-image of the orange, it's only a point, it's the orange itself, and F is stable outside the orange. Okay. In this case, the only stable singularities, it's a well-known fact that the only stable singularities in this case are just cross caps, triple points, and transversal double points. And a remark here is when you consider a stabilization of my map germ, the triple points in the cross caps that appears in the stabilization are isolated. So when you have just an F, we can shrink a finitely determinate map germ. We can shrink U if necessary, and we can assume that there are no cross-cut or triple points in the neighborhood, outside of orange, of course. Here's a typical example of a finitely determined upgerm. It's the cross-cut. And you can see here that outside the orange, the only singularities that appear in my surface are transversal double points. Okay, just a review. In this case, we are in the nice dimensions of matter, so we can consider a stabilization. And in the stabilization, if F is finitely determinate, we can count the number of stable singularities that appears in the stabilization. So in this case, we can count the number of cross-cups and the number of triple points. And these are independent of the stabilization taken, and they are analytic invariants of F. Okay. Here's an example to illustrate this notion. Here's the singularity A2 of the mode, defined by this map, this very no map, x, y cubed, x times y plus x5. And you can take it this following stabilization. Here is the generic fiber. It's generic for t distant to 0. It's the double point curve of this map for t different to 0. And you can see here the black points here, whose images are these black points. And you can see here a cross-cut here and a cross-cut here. And the triple points denote here the image of these 3 points. These 3 points, 1, 2, 3, have this image. And here you have a triple point. So in this case, the number of cross-cups is 2, and the number of triple points of F, when F is this map, is 1. So it's a very familiar surface. It's in front of the library. It's an exercise for each new student of the institute. Go outside the auditorium and in front of the library and count the number of singularities, stable singularities. Here's the one cross-cut. It's another cross-cut. And the triple point is in the other side. You need look in the up, okay? So in this example, the number of cross-cut is 2 and the number of triple points is 1, okay? Now we have the notion of finitely determinate map germ. We have a revision of this notion, and we saw 2 invariants, the number of cross-cups and the number of triple points. So I would like to define one more invariant. So to do this, it's convenient now to define what is the transversal slice of a map germ. Okay. So now I would take a map germ from C2 to C3, with the property it has cronk 1. It's a generic 1-to-1 finitely holomorphic map germ, and take a small representative. Here the condition about the cronk 1 is not necessary. It's just to simplify the result. You can consider also this notion for cronk 2 maps. And the notion is the following one. So take a plane denoted here by the letter H. And if H is generic, then when you cut our surface with this plane, if H is generic, then we call this transversal slice of F. The topology of this plane curve does not depend on the choice of the plane if it is a generic, okay? So this is the notion of transversal slice of F. Okay. And in the paper of Marar, Nunes, and Ballesteros in 2014, I think, they present a very nice result, which is when you consider a map germ from C2 to C3 in the cronk 1 case, we can consider the transversal slice. So it's the surface, the image of the map germ considered here, it's not necessarily finitely determinate, but we can move the plane along the surface. You can move this plane. When you move this plane, you get a family of curves. And the result of Marar Nunn Balesteros is f is finitely determinate if and only if this deformation, given by the moving of the plane, defines a stabilization of the transversal slice. So it's a very nice result. And so an example to make this more clear, we can start just with a plane curve, like this one here. This is the y square, comma y5. Now we can consider a stabilization of this curve. And you have the B2 singularity of the mode. Okay. So Marani and Balesteros defining in the same paper another variant, three variants, more precisely, denoted here by C of gamma, T of gamma, and J of gamma. So here we are taking stabilization of plane curves. So you can consider some singularities that appears in the stabilization of a plane curve. So C of gamma is the number of cusps that appears in the stabilization of gamma. T of gamma is the number of triple points, and J of gamma is the number of technodes that appears in the stabilization of gamma. And in this context, they prove that the first two invariants coincide with the number of cross caps and the number of triple points of F. So in this case, you can change the notation to avoid the confusion, also to simplify the notation. And I will call the number of cusp of the gamma by, I would denote by C of F. And here I would denote by T of F, just for avoid confusion, okay? And J of gamma, J of F, okay? Right. Okay, now some remarks about this term. It's well known that the invariant C of F and T of F are analytical invariants. And Marar and Noyo Balesteros also show that this new invariant J is also an analytical invariant of the map term J, F. And also it's well known that the invariants C of F and T of F are topological invariants in a family of maps. If you start with a F, a map term F, and you take a deformation of one parameter unfolding of the map, in this parameter, this unfolding is topological trivial, then the number of cross caps and the number of triple points are constant in the family. So they are topological invariants in the family. But we had another very nice result given by Fernandes Bobadilla, Penaforte Sanches, and Edson Sampaio, José Edson Sampaio. And they showed that the variants C of F and T of F are topological invariants just for pairs. When you consider pairs of maps, if the image of these maps are topological equivalent surface, then these invariants are equal, coincides. Okay. Now we can see here that we have three variants here, C, T, and J, and you have that C and T are topological invariants. So the question is, the natural question is the invariant J a topological invariant? So we can prove that this invariant is a topological invariant. And the answer is in the negative. So it's a paper in collaboration with Cidinha in 2017. It's from my PhD thesis. We consider in this paper a family of map terms defined here. It's x, y4, y6 plus yxy times y plus x y5 plus a deformation of strictly greater degree of in relation this part. Here, the homogeneous polynomial of degree 6, and here is a monomial of degree 7. So it's possible to show that that family here is topological trivial. And this implies that the invariants C and T are constant, but this implies that the surface given by the image of the map F0 and the surface given by the image of Ft are topological equivalent. But when you make a calculate of the invariant J in the level 0, we find the number 39. However, when you make a calculation of the J invariant, we find the number 38. So the conclusion is the invariant J is not a topological invariant. But there's something strange here. There's something that we need to understand. So look in the third coordinate. The third coordinate, we have a polynomial, homogeneous polynomial of degree 6. And here we have a deformation with degree 7. But what happens if you consider the same example, if you consider a genetic deformation in each coordinate with the same degree of the function's coordinates? So here it's degree 1. Here ht is a linear form here. Here gt is of degree 4. It's the same degree of y4. And here I will consider deformation when the degree of p is 6. It's the same degree of the third function coordinate. So when you make this exercise, we can show that in this example, the invariant J of f is constant for any t. For instance, we can check this with singular, and you can calculate the invariant J, and you can find 39. But it's not hard to show that it happens for any deformation with this property. So this gives a motivation to a question. The question is, if you consider a core-1 quasi-homogeneous finitely determinate map germ from C2 to C3, we also can write a core-1 map germs. You can also write in this form. And if we consider a deformation, one parameter deformation, one parameter unfolding of f, which add only terms of the same degree in each function coordinate. So with this condition, is the J of ft invariant constant along the parameter space? So it's a natural question, because when you look for this example, it's not the constant of the invariant J fails because this degree is strictly greater than this one. But if the degree is equal, the invariant J is constant. So related to this question, note that in this case, when you look for the genetic fiber here, the genetic the function, the map germ on the level t distinct to 0, it has a quasi-homogeneous map germ of the same time of f0. So another question related to this question is, when you consider a core-1 quasi-homogeneous finitely determinate map germ from C2 to C3, is the J invariant given by the weights and degrees of f? And this gives the motivation to study quasi-homogeneous map germ in this talk and this work. Okay, just a remark here. The problem of determining a topological invariant or analytical invariant given by in terms of the weights and degrees of f was considered for other invariants, and we know, it's well known that the invariants C, T, and the mu monomial of the double point curves are given by the weights and degrees. It's a very nice result of Mohn in 1919, and you can use this for find an answer for this question. And the answer is in the positive. Here's the formula. We can write f in this way, here the weight of x is denoted by the letter A, the weighted of y is denoted by the letter B, and the degree of the function's coordinate are denoted by the di with this condition. D2 is D3 is greater than D2, greater or equal than 2. So now the formula for the invariant J appears in this way. Here, there is something strange here because this is another letter which not appears in the description of CT and the mu number of DF. This is a index X, which assumes two values, 0 and 1. And I will explain this later, okay? Okay, before to understand this formula, or to say something about this formula, what is the idea of the proof? So very quickly, and it's not the complete proof, just some steps. First of all, we need consider a normal form for a quasi-homogeneous map geometry. We know that each rank 1 map geometry can write in this way. But it's not clear what terms appears here. What is the form of P and Q? So this lemma is not hard to prove that you can each quasi-homogeneous rank 1 finitely determinate map geometry. It's A equivalent to some things. So we can make a change of coordinates and express the map term in this form. Here, the term yn appears from some index n. And here, the term ym appears when the multiplicity is greater than 2. So we have this normal form. And this is distinct to 0 if the multiplicity of f is greater than 2. You can put 1 here, for instance. Okay, this is the first step. It's not hard to prove this. The second step of the proof is consider the relations about the invariants involved in the question. Here's another very nice result of Marara and Ballesteros. They express the invariant J in terms of the other invariants, the mu number of the double point curve, the cross caps, the number of triple points, and another invariant, very important invariant, which is the multiplicity of the double point curve in the target. Okay, so remember that we saw something about this. Where is the remark? Okay, here's a C, T, and the nominal number of the F are given by the weights and degrees. It's a result of mod. So here we have a formula in terms of weights and degrees of F. Here we have a formula, and here we have a formula. So we need to study this to solve the question. So we need to give a characterization of the multiplicity of the image of the double point curve in terms of the weights and degrees of F. So this is the way to prove this theorem, this result. So how this is made? How it can do this? So the second step of the proof is to consider different type of the double point curve. So the first type of the double point curve is called identification component. The definition is we consider a finitely determinate map geometry, and you take a representative, and you take a irreducible component dfj of df. If the restriction of f to dfj is genetically one-to-one, then we say that dfj is an identification component of df. Other Otherwise, if the restriction of f to the dfj is genetically 2 to 1, then we say that the f is a fold component of the f. So this is better explained with an example. Here is an example to illustrate this definition. Here you have the singularity C7 of the 1 given by x y squared, x times y cubed minus x7 times y. In this case, we have the double point curve have 3 branches, 3 irreducible components. df1 is given by this equation, df2 is given by this equation, and this forms a pair of identification components. You can see this in the picture. The red curve and the blue curve have the same image, this curve. And the black curve have this image. It's something like the cross cap, something like this. You have a curve here, and you take this. This is a fold component. Okay? Right. Now, the idea of the proof is to count the number of identification pairs of components and find a formula to count the number of fold components. And each irreducible components of df, we can find a parameterization, and with this parameterization, we can calculate the multiplicity of the image of this parameterization in the target. And the multiplicity is additive, so we can make a sum of things, and you get the multiplicity of the double point curve in the target. So it's a technical steps here. And here you can see that the multiplicity is given by this expression. When C is the minimum of A and D2, A is the weight of X, and D2 is the degree, weighted degree of the second function coordinate. And here again, we have the expression S. So let me explain something about this. So let's consider the canonical example of this talk. Not that when you consider the restriction and consider the image of restriction to V of X, this is 2 to 1. And the image is given by 0, y4, and y6. And in this case, the 0, x equals to 0, is an irreducible component of the f. So in this case, we have something like this, the plane, and the image is a cusp. The parameterization here of this curve is given by 0, u2, u3. We need to divide by 2 here because these are 2. It's not a primitive parameterization of my curve. If you consider another irreducible component of df, like dfj in df, in this case, each component of df is a line. We actually have 15 lines. df is a curve with 15 lines. So if you consider any other line, we have the image of this line is something like this. It's a coefficient here, another coefficient here, and you have something like this. U4, U6. And you can see that the restriction is 1 to 1. So Vx is the only fold component of this example, and the other lines are identification components. And you can see that the multiplicity of the image of an identification component in this example is 1, is a smooth curve. But the multiplicity of the image of the fold component is different. It's 2. It's a singular curve. So this is the reason to put this term here. S times A times B. A is the weight of X, B is the weight of Y, times D2 minus C. C is the minimum of 8 and D2. So we need plus this term here because when you have the appearance of a fold component given by the zero set of X, the multiplicity, it's not the calculate, the form of to calculate the multiplicity is a little bit different to the usual, okay? So you need to put this term here. And this value here, this invariant here, says that when a component, a fold component given by the zero set of F appears, when S is equal to 0, there is no component, there is no fold component given by the zero set of X. When the value is 1, so we have that V of V, the X equals to 0, is a component of the F. So this is the importance of this term here. It's to control this fold component, okay? Related to the question of the invariant J, there is another problem that I will consider in this talk, which is the embedded topological type of the transversal slice. So is the embedded topological type of the transversal slice given by the weights and degrees of F? So when you consider the transversal slice, let me find the image here. Here. When F has corank 1, the slice is an irreducible curve. So if the slice is a irreducible curve, so we can give a characterization of the topological type in terms of the characteristic exponents of the plane curves. And so just a minute. Right. So since gamma is an irreducible curve, the topological type of gamma can be characterized by the characteristic exponent. So this is the way to give an answer to this question. But the first thing to think about this is what kind of curve we can find when you cut a generic plane, when you cut the image of a quasi-homogeneous map germ with a generic plane. It's quasi-homogeneous. If F is quasi-homogeneous, the slice is quasi-homogeneous. So unfortunately, the answer is not. So here you have the same canonical example. In this example, after change of coordinates, we can find a parameterization of the slice, transversal slice. It's given by U4, U6 plus U9. And you can see that the characteristic exponents of the slice, or the genetic section, are 4, 6, and 9. And of course, this is not a quasi-homogeneous map germ. It's not a quasi-homogeneous curve. So the conclusion is that the transversal slice may be not quasi-homogeneous. So in some case, they are not. They are quasi-homogeneous, but maybe not quasi-homogeneous. However, it's not a problem to give a question. It's not an obstruction to give a precise answer to this question. And you can use the same technique to study the behavior of the multiplicity of the double point curve in the target. And using the same technique, you can find a positive answer to this question. Okay, so the answer is the following one. Here we have a result. Uh, F is the same as above. It's a crank one, finitely determinate, and quasi-homogeneous map germ. And C is the minimal between the weight of X and the weighted degree of the second function coordinate. So first condition is if the D2 is greater or equal than A, and the D2 over B is greater or equal than 4, and the greatest common divisor of D2 and D3 is equal to 2, then the transversal slice has 3 characteristic exponents given by D2, D3, D2 plus D3 minus A. This is exactly this example, the case of this example. Here, we are in these conditions, in this hypothesis. This hypothesis happens. Note that the degree of D2, D3 is equals to 2. Here you have 4 and 6. So the great common divisor of 4 and 6 is 2. And the other conditions also happens. And we have 3 characteristic exponents, 4, 6, 9, which are given by D2, D3, 4, 9, 6, 4 plus 6 minus 1. So this given 9. Outside this strange case, outside this not usual case, the transversal slice is quasi-homogeneous. So it's parameterized by something like this. UK1, UK2, and K1 and K2 are the characteristic exponents of the transversal slice, and they are given by these two expressions, D2 over B and this expression plus 1. Again, we have the influence of the fold component given by x equals to 0 in the source. Okay, so the proof is some technical. I will avoid to explain technical details, but the idea is to divide it in several cases determined by the relations of the degrees, which appears in the normal form of quasi-homogeneous map germ, and study change of coordinates. Just this case is it's hard. This case is not hard to prove. Okay, it's not hard. It's not so easy to see this. Okay, interesting corollary of this result is the following one. If you consider F as above, a finitely determinate correct one quasi-homogeneous map germ, and you consider one parameter unfolding, if this one parameter unfolding adds only terms of the same degrees as the degrees of F, then F is Wittig singular. So this concept is a corollary of this theorem. It also can be viewed as a corollary of the first derivative of the invariant J, due a result of Marari and Nueva-Leceros, which gives us characterization of Wittig singularity in terms of the constants of the three invariants, C, T, and J. Okay. Now, after to prove these results, we would like to research to generalizations of these results. What about the Correct 2 case? It's true. The questions made here, it's true in the Correct 2 case. So when you consider the same question to Correct 2 case, the question is the embedded topological type of the transversal slice of F determined by the weights and degrees of F in the Correct 2 case? So the following example shows that the answer to this question is in the negative. So here, I present 3 map germs denoted by G1, G2, and G3. Note that G1, G2, and G3 are homogeneous, and the degree of the first coordinate is 2, 2, 2, 3, 3, and 3, 5, 5, and 5. So each map germ is a homogeneous finitely determinate map germ of Corancun of same time. So a remark here, these are reflection maps introduced by Penaforte Sanchez. It's a very interesting paper. And we have this table. When you make a calculation, you find that for the first map, the map G1, the transversal slice have two branches. The first branch have 3 and 5 as characteristic exponents. So the parameterization is something like this: is 3 and 5 with some coefficients here. The second branch of the same transversal slice also have 3 and 5 as characteristic exponents. And it happens the same for the D2. D2 also have two branches. The transversal slice have two branches. Each branches have the topological type given by the characteristic exponents 3 and 5, 3 and 5. But in this case, the topological type of a curve, of a non-irreducible curve, is characterized, it's given also by the intersecting multiplicity. We need the two information to determine the topological type. So when you calculate the intersecting multiplicity of the first example, the intersecting multiplicity between these two branches is 15. In the second example, the characteristic multiplicity of these two branches are 16. So they are not topological equivalent. They does not have the same type, the same topological type. In the third example, it's a little bit strange. The transversal slice is irreducible and has three characteristic exponents given by 6, 10, and 11. So in Corancun case, it's not true. The topological type of the transversal slice is not given by the weights and degrees of F. Okay, but as a good researcher, we think about these questions and say, so Corancun, so it's a special condition. Corancun, it's fair, but Corancun is a special condition. So let's consider the problem for other dimensions. So let's consider the problem for a map germ from Cn to Cn plus 1 with n greater or equal than 3 with the same hypothesis, Corancun, quasi-homogeneous, and finitely determinate map germ. And we have two questions here related to the problems that I told in this talk. The first problem is the embedded topological type of the generic hyperplane sections of F determined by the weights and degrees of F? And the second question is a one-parameter unfolding F of F, which adds only terms of the same degrees as the degrees of F, is Wittig singular? So the same questions, but in a general context. So in the context of a map germ from Cn to Cn plus 1. And again, the answer is in the negative. So here I have a very classical example, is a demos example. It's a map germ, it's a family of map germ from C3 to C4. This is a topological trivial family of map germs. And in this case, we can note that the deformation has own terms of the same degrees, weighted degrees. And each FT is a Corancun finitely determinate map germ of the same type. So we have all the hypotheses that we ask. However, this family is not singular because the family of double point curves in the target is a Brillanson-Spader example. So also we can check that the generic hyperplane sections, gamma 0 and gamma t, have distinct embedded topological types. Okay, this is not, Corancun is not a special condition in general, just in the case of C2 to C3. And to finish my talk, another application of this technique, these results, not directly of these results, but the technique itself, It's the following result, which is a particular case of the Zarisk's multiplicity conjecture for a pair of no isolated singularities. Yesterday you had a very nice talk given by Thomas Pelka about the proof of the Zarisk multiplicity in the case of families of isolated singularities. And here have a very small contribution. It's a work in collaboration with my PhD student, Milena Gama, from Universidade Federal da Paraíba. And we are able to prove that if you consider a map germ F and G from C2 to C3 as above, if the image of F and the image of G, which are surface, if these surfaces are topologically equivalent, then the multiplicity of F and the multiplicity of G are equal. So this question was made by Edson Sampaio in Mexico in 2 or 3 years ago, and this is the answer. Yes, okay. So thank you, Edson, for the question, and it's all. Thank you. Happy birthday, Saiki.
Any question? Yeah, there is a question there.
Hi, thank you for the very nice talk. Okay, so I have the following question. The cross caps and the triple points, you can identify them in the multiple point spaces, the multiple points, whatever.
Uh-huh.
So I wonder, what is the connection between the J invariant and the multiple point spaces?
What the definition of what? Sorry.
What is the connection
What is the connection?
between the J invariant and multiple point spaces, if you know there is one or something?
Okay. This is a very nice question. There is a remark in the paper of Marara and Nueva Ballesteros that they relate the invariant J with the polar multiplicity of the double point curve in the target. So the first polar multiplicity of a point in the target is related with the invariant J. It's not clear for me if it's equal or not, but it's very related with the polar multiplicity.
Okay, thank you.
Any other question?
And the formulas relating with the image Milnor number? Mararmon type formulas relating J with the image Milnor number.
Image Milnor number. What is the relation with the image Milnor number? I don't know.
Because I don't remember well, but there's also another invariant in Mond's article,
yes.
N.
Yes,
Okay.
yes, I remember now. There is a formula which relates the image Milnor number with these four kinds of events. There is another formula of the image Milnor number using these three invariants. I'm not sure, but there is a formula.
Okay. Thank you.
Yeah. Can you tell us the hypothesis in the question you made to Edson? So for which maps that works?
This is a work in progress. Here, okay.
Like the as above. I want to know what is as above.
As above. As above means Kroc 1, finitely determinate, and quasi-homogeneous. But Kroc 1 is not an obstruction. We can avoid this hypothesis, but we does not have a proof in the Kroc 2 case. Just in Kroc 1 case.
And do you have counterexamples if you remove some of these hypotheses?
No.
Okay. Thank you.
Can you go back to the formula of the J invariant, please? Can you go back to the formula of the J invariant?
The formula of J invariant, okay. Let me see.
Yeah, because precisely what I suggested is just a generalization of this theorem where you use these three invariants.
This formula.
So the thing is, mu, the Milnor number of the double point curve is not something zero-dimensional. Okay, it is a core, whatever. But this J, it is. So I ask you because maybe you have a very easy generalization to higher dimensions or something if you find a good relation with the multiple point spaces. And that's it.
Okay. Thank you.
Any other question outside Valencia? Okay, so if not, let's thank the speaker again. Sorry, I didn't.
Thank you. With respect the result about Whitney singularity is
The polarity.
the converse is
Let me find this. Yes, this one, right?
yes, this is optimal. Is you have a counterexample in the converse case. You have this, if you add on terms of same degree, you have a Whitney X singularity.
Yes. But outside the same degree.
Yes, it is. If you Whitney X singular, so you conclude.
Yes, we have a counterexample. If I understand your question, is outside this. If you consider this deformation, so it can prove that this deformation is topological trivial, but it is not Whitney singular. And the point is, this case, when you look to F0, the F0, the image of the double points have seven smooth branches, and another one which is singular. And this singular branch is the image of phi of x. Now, when you consider the deformation from t different to 0, we have now the same 7 smooth branch, but now this red curve is now a smooth curve. Then the multiplicity here is 9, because this is 2, and here we have 7, and the multiplicity here is 8 to t extends to 0. And when you looking for the Whitney singularity, so the family of curves should be Whitney singular. This implies that the multiplicity should be constant. In this case, the multiplicity is not constant, so this family is not Whitney singular.
Okay, thank you.
Any more comments? Question? So let's thank the speaker again. Thank you, Antonia. So we start in
Good afternoon. It's my pleasure to introduce our next speaker. He's Christian Muñoz Cabello. He's a PhD student at University of Valencia in Spain, and his research involves topics related to singularity theory and differential geometry, with emphasis on classification of frontal singularity germs. The title of his talk is Singularities of Frontal Surfaces.
Good afternoon, everyone, and thank you for coming. As the presenter said, the title of my presentation is Singularities of Frontal Surfaces, and in here, we will treat a rather similar topic to that treated by Medina Tejero this morning, only that his work is in a more geometrical sense, in a more traditional geometric sense, and my work is more focused on studying the topology of frontals. Now, let's start by a small motivation of what are frontals. Now, the archetypical example, or at least my favorite example of frontals, are the equidistants. The equidistants can be found described, for example, in Arnold's 1990 books. To motivate them, let's consider that we have a pond, and we throw a rock into it. Then, in the surface of the water, we will see how a series of ripples start to emerge. These ripples can be interpreted as physical waves traveling through the water. But if the pond is small enough, the waves will bounce back and start to clash into one another. These waves, or rather these wavefronts, usually will generate shapes such as the cusp and the node. In particular, the cusp and the node are what is known as the stable frontal singularities in curves. Now, some places where we may find frontal hypersurfaces. For example, light cardioids, which are formed when this is probably you're familiar with it, when you have a cup of water and you are outside in a terrace and you have a cup of water and the sun shines right through it, then it will form a series of shapes. These are similar to the equidistant we have here. We could describe, well, the equidistant is kind of a standard model, but that's outside the scope of this talk. We can also find them in control systems, such as what I imagine Giovanni was trying to talk about last week. We also have, this, for example, was two-dimensional. We can move on to 3 dimensions, in which case we have, for example, the sound barriers, which are produced by perturbations in the air caused by planes reaching a certain speed. This is not like, there is a short anecdote. There is not such a thing as a sound barrier. It is just, this barrier is just the clashing of the air waves, which are too close to one another to produce a popping sound that characterize air jets and stuff. And a little more unrelated example, which corresponds to the mother theory of frontals, which is contact structures on contact manifolds, which is that we can prove Huygens diffraction principle using the same theory that gives rise to frontals. The proof can be found on Gage's book, Introduction to Contact Topology. It is, I consider it a rather mild introduction to contact topology, although it goes very deep. But the proof can be found there. Now, my talk in particular, or well, my work in general, is based upon the works of Go Ishikawa and his theory of infinitesimal legend equivalence. Among other things, Go Ishikawa proved that Courant 1 stable frontals come from a certain family of maps called the open Whitney umbrellas. Bear in mind, it is not that every frontal comes from one open Whitney umbrella. It is just that open Whitney umbrellas generate all frontals, all stable frontals in Courant 1, just like matrices give us the determinantal singularities. Now, another result from Ishikawa is that stability is codified in terms of a certain C algebra Q. We will not discuss it, but I think it is an interesting tool, which I have been working on with my thesis advisors. And and he introduces the notion of legendary codimension, which measures how far a frontal is from being stable. Think of it as the equivalent notion of stability we had in the ISIS course. Now, as you can see, this Ishikawa has a great breadth of work. It is no surprise that Les Wilson called him Mr. Smart. And now we move on to the start of the work itself, frontal equivalence. Now, to give a more proper modelization of frontals, a map F from Cn, a hypersurface germ F from CNS to Cn+1 is frontal. If we can find a differential one form, from nu, such that it doesn't vanish along F, and it verifies a certain normality condition. This condition here basically means that wherever we have points, we may not have a tangent space. For example, if we run across these blue lines, we have tangent space well defined, except along this folding on this cuspidal edge. However, we can define, we can consider a normal line, which is well defined, and it has a certain notion of smoothness, which once again allows us to define a Whitney stratification along frontals. And now we expose a result which says that two maps, F and G from CNS, Cn+1, if they are A equivalent and one of them is frontal, the other is frontal. This was already known by Arnold. However, he does not give a constructive proof. I gave a constructive proof on one particular case, since it allows us to later go, let's say, up and down between the contact world and the world of frontals, of pure frontals. So, moving to stability, an unfolding F of uppercase F of F is frontal if it has a frontal representative. We already know what unfoldings are due to the ISIS course. And in particular, we will say that the map F is F stable if every unfolding which verifies this frontality condition is trivial. This is that can be reduced via A equivalence to the map F times a series of variables that do not intervene with F. Now we construct this vector space, which is given by, we take frontal unfoldings of one parameter and then take the diversity vector at time t equals 0. And we will call this space French F of F, or just the frontal infinitesimal deformations. In particular, we have that it contains what is called the A tangent space, which are the deformations that are trivial under A equivalence, which is one of the usual notions of equivalence we use in singularity theory. Now, we say that F is F finite if the dimension of this quotient vector space is finite. This is similar to the role of the Turina number in hypersurfaces given by an implicit equation. And similar to the notion of A codimension, my colleague Jimenez Conejero presented yesterday, in fact. Okay. Now, we characterize frontal stability to give it a more geometric definition. A more geometric vision. And a current one frontal is stable as a frontal if only if it has frontal codimension 0. This is the notion of frontal codimension measures how far this frontal is from being stable. Just like in Ishikawa's theory, we have the gender codimension. In the theory of pure frontals, we have frontal codimension. And now a more geometrical criterion. This is what I like to call the frontal Mader-Gaffney criterion, since it is a frontal version of the Mader-Gaffney criterion, which says that a Corrang one frontal surface F is F finite if only if we have a finite representative F. This is a finite representative such that if we just outside the origin, it is frontal stable. Later on, we will see some examples of frontals which verify this condition. Now, finiteness in the real case is a little more technical to define, but in the complex case, it simply means that the preimage of 0 is 0. Now, some examples of frontals we can see. This table is part of Mons classification simple for surfaces in C3. We have 4 of the 5 families, such as the birth of K crosscaps. Some of their properties were studied by Mons in 1985, and they verify a general formula in this form. This was also proved by Mons, because a full surface simply means that it has first and second component xy squared. Mons proved that the third component can be codified in this way. And now we apply what we call the frontalization process. This is, in the third component, instead of taking y, we take y cubed. So for example, in this table, the function p stands for DS functions, in its case. And now, for the frontalized version, we are multiplying by y squared. Now, here are some examples. As we can see, these are some of Mons surfaces, simple surfaces, and these are the frontalized surfaces. Note how we go from having a round top, besides having some pinching, to taking that pinching and forming a crease. This now can illustrate the frontal Mother-Gaffney criterion. Since we can see that here we have a crease, which this will turn this surface into something having infinite codimension in the classical case. However, in the frontal case, this is perfectly good, perfectly viable, because the cuspidal edge, this is the creasing, is actually a stable singularity. Now, some properties, a quick rundown of some additional properties, is that this procedure will only produce wave fronts in the case of the cuspidal edge and, of course, immersion. A cuspidal edge wave front simply means that it is the kind of frontal that will emerge in nature. And the A codimension of a simple four surface is going to be equal to the F codimension of its frontalization, which I denote with a check. Well, in fact, even if F had infinite codimension, its frontalization will have also infinite codimension. This is preserved both ways, finite and infinite. Now, regarding double point space, we will explore the double point space in more detail later on, but just saying that frontalizing a full surface introduces creasing, cuspidal edges, and that the transverse double points are preserved. And now, just to say that, to give a little more geometry into this talk, we can define an extended Gaussian curvature on the frontal folds. This extended Gaussian curvature was introduced by Saji Umehara Yamada in their 2009 article, the geometry of fronts. Now, up until now, we have discussed monogerms. Also, here there should be a 0. But given a frontal monogerm F, we define this space. And now we say that a frontal multigerm is F stable, or, well, sorry, stable as a frontal or F stable. This is redundant with this. If and only if its branches, which is simply changing the multigerm for monogerms, are F stable and their sets and the sets tau meet in general position. Now, in the classical theory, the taus represent what is the tangent space of what is called the isosingular locus. So we conjecture that the same should happen in the frontal case, but time caught up with us and we couldn't go over all of the details, but we believe it should be proven this way. Now, let's see how to generate some examples. Wavefronts can be obtained as discriminant of maps with a small, with a smooth critical set. This is also easily deductible from Arnold's work. And frontals can be generated taking analytic plane curves, which are always frontal, unfolding them, and applying a certain frontalizing condition to their parameters. In particular, the unfolding will have rank 1, and the condition is pretty simplified. And now there was a sort of conjecture by Nuño Ballesteros, which said that if we in particular take a versal unfolding, the frontalization is going to be versal within frontals. And indeed that's going to be the case. But let's formalize this process a little more. Given an unfolding of an analytic plane curve, we define the pullback as this map. This is we change the parameters of the unfolding according to a certain function h. And now, in particular, we have the conjecture of Nuño Ballesteros is indeed true. This is this alteration, this twisting of the parameters. If the parameters h can be given as a graph of a certain map, and in particular, this certain graph verifies that the induced map is miniversal as a frontal. This also gives us a formula to compute the frontal codimension of a analytic plane curve, which in particular, this formula it is fundamentally using the Puso parameterization, which can be found on De Jong and Pfister or in Wall's book. And any corank 1 frontal hypersurface admits a stable frontal unfolding, as long as this has an isolated instability. This is simply so that the curve we're taking is not degenerate. Now, this is from this point onwards, we have 10 minutes left, but those who have assisted to previous lectures, to previous presentations by me or my advisors, are already familiar with this talk, with this part of the talk. This is simply the double point space of frontal surface. We define the double point space of F. If we assume F has corank 1, we can simply divide the differences, which solves the issue presented by the usual definition of the double point curve, wherein you need to take the closure, you need to be careful of some trivial points. Some of the issues are taken care of simply by this construction, which gives us a curve in free space. And now we project it onto the plane via simply the projection that removes the component y prime. This in particular induces a complex structure, which is kind of like saying it induces a scheme, which is like saying that D2F induces a scheme over DF, its projection, but in the complex case. And now there's a result by Marar and Tari from 1996, which says that for wavefronts, we have a certain decomposition for the generating function of the double point space in the source, the projected one, which decomposes it into the cuspidal curve and the purely transversal double points curve. More generally, we have that this formula holds for any frontal. This is because Marar and Tari were not so much focused on wavefronts as they were on discriminants of certain maps. However, discriminants and wavefronts are two sides of the same coin. This is any discriminant can be considered as a wavefront anyway. So, of course, there was a question of whether this equation calls for pure frontals and not just wavefronts. Now, we have a further results regarding this function. We have if we can characterize whether f is f finite, or even if it is just a cuspidal edge of a curve of transversal points, in terms of which form this lambda function takes. As a consequence, we have that there are only, here they are. There are only 6 stable, frontal stable surfaces in 3 space. Of course, I am excluding the inclusion because that's one's trivial. And we have, for example, the cuspidal edge, double point, triple point, the cuspidal double point, the swallowtail. All of these are already wavefronts, so that's no news. That was already normal Arnold. But we also have the folded wing umbrella or folded crosscap. Now you can see that all of them have either creases, intersections, or both. And in particular, the swallowtail is the one that maybe it's the one with the more interesting geometry, but I only care about the topology. All of them are beautiful for me. So, as an example, let's analyze the swallowtail. We have the swallowtail can be parameterized in this way. If we open the computer, go to Oscar, ask it to compute the double point space, we get this result, and this result decomposes into these branches. Note that the cuspidal edges, of course, always have multiplicity 2, because the cuspidal edges are, in a way, a limit of transversal double points. And the pure transversal double points only have multiplicity 1. Now, this multiplicity 2 is going to cause an issue if we try to compute some Marmon type formulas, and I'm almost out of time. So whenever the organizers want to stop me, I will just go through the rest. Simply say that a smooth family is a frontal stabilization if it admits a frontal stable unfolding in one parameter. And then a result. Oh, sorry, this is not a result, this is a definition. Okay, if it has here it is. This is what I was looking for. If it has a result in stability that admits a stabilization, and we call the image of the stable unfolding, we call it the frontal disentanglement. Now, a result proved independently by Ley and Siersma states that in this condition, then this disentanglement, this image, has a homotopy type of all spheres. This is because we are taking a stable unfolding, and well, then we have some form of Marmon formulas for frontals. As you can see, we had to split. There it is. Now we have to split into the formulas into cuspidal edge and pure transversal points. Why? Because the Milnor number, if we try to compute the Milnor number of something which has an accumulation of double points, it is going to go to infinity. This is simply due to the fact that it will count the number of multiple points. So of course it's going to count infinite double points. So we need to split it in 2 parts. And now Diaz invariants that we show here, we have swallowtails, cuspidal double points, triple points for the wing umbrellas. Recall that Diaz are the stable frontal singularities. And in fact, they are the zeros. They are the ones that have codimension 2. This is their isolated frontal singularities. Diaz invariants can be computed using a program I wrote, which is available on my GitHub. It is for Singular. Sorry, Matthias. And I will, as soon as I have access to a computer, because my computer is not working correctly right now, I will work on an Oscar implementation. Now, just mention that consequence of a result by Jimenez Conejero and Nuño Ballesteros from last year allows us to say that the oh, sorry, I didn't define this. Okay, so the number of spheres in this wedge is we call it the frontal Milnor number. This can be computed, for example, using Siersma's method of deformations. In particular, this value can be easily reduced to be equal to the image Milnor number in a plane curve minus the number of cusps. Why? Well, if we okay. Whenever you want to stop, really, I don't want to. Okay, so if we have, for example, this is A6, we can deform it. This is stable, but not stable in the classical sense. This gives us here a 1, However, here we have more homology that have been developed. So if we develop it completely, we get this number, which is 3. However, we have 2 cusps, just choose identity. The more interesting result, the more suggested case is perhaps in 2 dimensions, wherein we take a Corang 1 frontal surface with its instability, and we once again see the usual aspects, the swallowtail, the folded wing umbrella, the triple points, and we have a formula for the number of spheres in a surface. Now, this is the moment of a frontal surface. Now, I think this is the end. Just say that now that we have a frontal minor number, it is part of the course to try and do a frontal version of Mount conjecture. Recall that Mount conjecture says that if f is finite, then the image minor number is greater or equal to the equal dimension, with equality if and only if f is quasi-homogeneous. And in the proposed frontal version, we simply state the same, but changing image by frontal, equal dimension by frontal codimension, and so on and so forth. And for example, in the examples shown earlier in the table, all of them verify this inequality with identity. Why? Because they are quasi-homogeneous. Muito obrigado. Eso es todo.
Thank you very much, Christian. Are there questions?
Hi. Just a question. In the slide of the, well, you give a formula for the frontal codimension related to the eco dimension.
Yes.
Is that for, yeah. That is in general. It's not for Corang 1, it's in general, isn't it? Or is for Corang 1?
No, this formula refers to an analytic plane curve.
Okay, nice.
It's for
Thank
curves. So, of course, they're Corang 1 by necessity.
Thank you, Christian. Very nice talk. Do you have a characterization of the space of F deformations, or you have a characterization in classes of frontals? Do you have in general? Can you say what are the F deformations? Given a frontal, can you characterize what are the deformations that give frontal?
So most of what we have is this expression. Now, we also have the open window umbrellas different by Ishikawa, which are given above, but we can use a family of projections to obtain all of the frontals. However, it is true that we do not have all the families of projections either. So in general, even in Corang 1, although that we have in Corang 1, sadly we don't have an idea of what a generic deformation of a generic frontal looks like. This is mostly because the frontal condition, even in Corang 1, is rather complicated to compute. It requires to check, like, for example, if in Corang 1 we have something in the form f of x, y, where x can have n variables, and pxy, qxy. If we take the non-free variables to speak, then this is frontal if and only if q sub y, if p sub y divides q sub y or q sub y divides p sub y. And now, this condition, which is simple to state, it quickly devolves into lots of computations.
More questions? So we want to thank you again. Thank you very much. So we have a talk in the sequence. it's a great pleasure to introduce our next speaker. He's Wojciech Domitry. He's from Warsaw University of Technology in Poland. And I'd like just to say that, as many of you, Wojciech is another example of a very important collaboration with the Singularity Group, very many members of our group here in São Carlos. So thank you very much, Wojciech. So out and loud, the title of his talk is Singularities of the Gauss Map Components of Surfaces in R4.
Thank you, Irma. Thank you, Miriam. It's very nice to be here, and it's very nice to be here celebrating the 60th birthday of Osamu Saeki. And it's very nice to be here again in San Carlos. It's a very important place for me, for my research in mathematics and friendship with Brazilian. So I'm very happy that I have possibility to speak here. And thank you for organizer to give me this possibility. And also I thank you because it's also helped me in research very much. Okay, so I will talk about subject which is quite new for me. This is singularities of Gauss map components of surface in R4. This is the joint work with Yvonne Hernandez Martinez and Federico Sanchez Bringas, which are experts from my point of view in this area. Okay, this way. Okay, so I will define what is the Gauss map. So obviously you all know, but I will define it anyhow. So we have a smooth oriented surface and we have immersion of the surface in R4. And the Gauss map is just for a point. Oh, sorry. This way. Okay. For a point, yes, we map point to the tangent space, which lies in R4. So we have a map from a surface M to the Grassmannian of oriented two-dimensional subspaces of R4. This subject was studied by many people. I think the first one who studied was Wilhelm Blaschke. And he wrote a paper in 1949, Austrian mathematician. And then 2 years later, the same results was proved by algebraic topological method by his student, Chern and Spanier. Yes, Chinese and American mathematicians were both in Chicago at that time. Okay. And in fact, we use, in the 80s, there were Hoffmann-Ossermann and by the German mathematician Weiner. And Hoffmann-Ossermann was the first paper that we studied. They are people from complex analysis, so they used the method of complex analysis, which were quite complicated for us. But when we come back to the original approach of Blaschke and Chern and Spaniel, you see that problem is quite easy to understand. Okay, so first I will describe the structure of the oriented Grassmannian 2-4, following the paper by Chern and Spanier from 1951. So we have a positive orthonormal basis for R4, and we have an oriented two-dimensional subspace V. Yes, and we use the Flickr coordinates of this Grassmannian. So what is this? So we just take a positive orthonormal basis of V, and we describe the just by vector, yes, V1, V2. In this basis, it has 1, 2, 3, 4, 5, 6 elements, yes, and then that you see this is not a arbitrary element of these bivectors, because it says just decomposable as a wage product of 2. To satisfy this condition, this first condition has to be satisfied. This condition is just such element which the same element is equal to 0. And the second is we just extend the inner product, yes, the dot product, from R4 to the by vectors by the usual way using the determinant. And then this means that V1, V2, the norm of this in this inner product on bivectors is 1. Okay, but if you use another orthonormal basis in bivectors on R4, this basis, you see, is x1, y1, x2, y2, x3, y3, and you write v1, wage v2 using this basis, when this previous two equation became this equation, in this new basis. So we got just two spheres, which lie in R3, two-dimensional spheres. We can even say what is the radius of this sphere. The radius is 1 over square root of 2. So the Grassmannian, oriented Grassmannian to 4, yes, Grassmannian of oriented two spaces in R4, I should say, has the structure of the product of two spheres of the radius 1 over square root of 2. Okay. So then we have how the Gauss map looks like. Okay, so we have this map, yes, but this map has two components because it is a map to the product. So we have these two components, GI and G2. Yes, this is just composition of the Gauss map with the projections. So the Gauss map can be written in such way, the Gauss map, yes? Okay. How they looks like. So we now use something which we call local Darboux frame on U. So what we mean? So we have a positive orthonormal frame such that at any point, this we have on some open subset of M, yes, and for any point P in M, yes, we take that E1P and E2P is a positive basis of TPM. It is, of course, orthonormal basis of TPM. And the Gauss map is just, if you use these flicker coordinates, it's Gauss map restricted to U is just E1, wage, E2. And the components is just these things. It is just 1/2 of you take the orthonormal basis of the tangent space and add the what? What this is just the orthonormal basis of the normal to the surface at this point. And in these new coordinates, it is 1 over square root of 2 x1. And G2, the same, only you subtract. And this is 1 over square root of y1 in these new coordinates which we introduced. So the map is very easy to write at least. And from this, we can get very easily some result which was obtained by Blaszke and other people by Weiner. Yes. Now we use the method of moving frame. So this is the basic things. You can find these things in the excellent book by Alfredo do Carmo. Yes. So this is just, we take this immersion, the x is just E1, E2 are the tangent vectors. So this is the dual basis, θ1, θ2. When you differentiate d E1, then this is the connection one forms, yes. They obtain by just projection because these all bases are orthonormal. From this, that the tangent space is given by E1, E2, you got that E3, E4 are equal to 0 on M. And also because this is orthonormal, this is dot product, and they are orthonormal, we get this. So from this, you got that omega II is equal to 0. And this is the first and the second Cartan structure equation obtained by differentiating this and this again. Okay, and then we have the definition of the Gaussian curvature. Yes, the Gaussian curvature is just if you differentiate d omega 1, 2, yes, then it is minus Gaussian curvature θ1, wage, θ2, θ1, wage, θ2 as the area form on our surface. And the same, this is the definition of the normal curvature, just d omega free 4 is minus normal curvature times the area form. Okay, so this is classic things. And now, what we can say about the differential of the Gauss map? Because the Gauss map is going from surface to the four-dimensional manifold. So we can expect it that generically it's an immersion. And it is the case. If you look, if you take the differential of G, then you obtain this. Yes? So when it's not immersion, all these coefficients vanish at this point. Yes? No, if the dimension of the space, no, if the dimension of the space is 2, if the dimension of the space, if they are linearly dependent, if the dimension of the space is smaller than 2, so it's 1, it's not an immersion. It is this condition you can find also in the paper by Little in 1969. He proved that it is not an immersion if the Gaussian curvature and delta at this point are equal to 0. This is equivalent condition. And this condition, so generically from this we can obtain that this is generically, this is immersion. The Gauss map is an immersion, yes? And the generic condition is just this, yes? That at no points the Gaussian curvature is equal to 0 and the delta is equal to 0. Okay, so there is nothing to do from the point of singularity theory. You get immersion generically, but we have these two components. And what we did, and we hope nobody did it before, at least we haven't found it, we studied the singularities of the components of the Gauss map. Okay, so now I recall the definition of the normal and the Gaussian and the normal curvature, yes? And just if you add the Gaussian curvature to the normal curvature, yes, and take this area form, just adding these formulas, then you obtain such wedge product, yes? And if you subtract them, then you obtain such wedge product. So what we know? So we know that the Gaussian curvature plus the normal curvature is equal to 0 if and only if these two one-forms are linearly dependent. They are forms on M. They are forms on our surface. Yes? And this, if you subtract Gaussian from Gaussian curvature, normal curvature, it's equal to 0. So they are equal, in fact, if these forms are linearly dependent. Why I did this calculation? Because if you calculate this is G1, G2, the components. If you calculate the differential of G1, of the first component of the Gauss map, then you obtain the same, exactly the same one forms as a coefficient. And if you take the differential of G2, you obtain the others two forms. Yes? So the kernel of G1 is exactly the Pfaffian system defined by these two one forms that we have previously. And the kernel of G2 is exactly the Pfaffian system, yes, defined by these two other one forms, yes. And if you look at this equation, so what we get? We can take x2, x3, y2, y3 as a good base of our space in which we have these two surfaces. So, in fact, if you want to calculate the Jacobian of G1 from this formula and from the previous formulas, you get that exactly the Jacobian of G1. What I mean by Jacobian, I have Gy. This is a map from the surface. This is the area form to one of the sphere, Si, with the area form on the sphere. And I take the pullback by Gi of the area form on the sphere, obtain some function plus the area form on M. And then you see what in this way can be obtained, and this is it was obtained by Blaszke, by Weiner and Hoffmann-Ossermann, that the Jacobian of G1 is just 1/2 of Gaussian curvature plus normal curvature, and Jacobian of G2 is 1/2 of the Gaussian curvature minus normal curvature. Okay, so we know what the singular set of G1 and G2. But we want to what we want to prove. We have a map from a surface to a sphere. So we think that what will be singularities will be fault and cusp, but we want some condition where will be fault, when will be cusp. Of course, if we want generic conditions, so this is the obvious first generic condition, that we take differential of the singular set, yes, given by a function, and restricted to this is not vanish, yes, so this is a smooth curve. And then this is the kernel of GI. This is the kernel, this Pfaffian system, the solution of this Pfaffian system is the kernel, and we want that this is transverse to the singular set of GI. This is the singular set of GI, the Jacobian of GI, yes? Except at a finite number of points when it is one tangent, so when we have cusps. And also, if you want to have stable singularities, we assume we have only transversal self-intersection, yes, on the set of singular points, yes, and we do not cross the cusp point. So this is this condition. For any P and Q such that it is on a singular set, if GIP is equal to GIQ, then this Pfaffian system is transverse, the solution of this Pfaffian system is transverse to the curve at P and Q, so we have a fault. And if you take the image of the tangent space to the singular set, this is transverse to the image at the other point. Yes, so we have only transverse intersection and we have no triple such points. So this is our generic condition. And under this condition, we can prove that the only singularities are fault and cusp, and we have only transversal intersection of the set of singular points, and no triple by double, and only in a cusp point. In faults, never in cusp. Okay, so how we prove it, that this genericity? So we just put locally the immersion as a graph, yes, when this is G1, G2, and this is how they looks like. This is after, because this is a map to S2, so we use the stereographic projection, yes. So this is these maps, yes. Quite complicated for calculation. In fact, to prove this theorem, we need to use some computers, but fortunately not Singular, neither Oscar, but we use Mathematica a lot. Yes. And then theorem is the following. Properties 1, 3 are generic, and if M satisfies 1, 3, then GI is stable. And we prove it just usually. We have this graph F, yes. This X is given by the graph of F, yes. Then we have a map for gamma I from the 4-jet of F to the 3-jet of GI, and we prove that this is submersion, yes. So since this is submersion, for this we need to use Mathematica to calculate it, because you see this G1, G2 is quite complicated, because we have this H, and the H is here, and also RP, and 1/, so it was quite complicated to calculate it. And what we get also, we can obtain it using the result of Saji Umehara Yamada, since the map, which has only fault and cusp, from two-dimensional surface to two-dimensional surface, is an example of coherent tangent bundle. And when we have a Gauss-Bonnet formula for this map, yes, so this is Gauss-Bonnet type formulas. So we have the assumption M is an oriented closed surface, yes. We have the immersion, and we assume only properties 1, 2. This are only needed. Then we have the following formula. 2 pi times the Euler characteristic of M is equal to the integral over M, over our surface. This is absolute value of K plus minus K, Gaussian curvature plus minus normal curvature times the area formed on our surface, plus 2 times, and this is the integral over the singular set, and we oriented the singular set in a such way that if you are moving, so this is the sphere, yes, so this is in an image, so you have the image on the left hand side, so in this way, yes, if you are going on the, so we orient it in a such way, and here instead of the singular curvature, in this case, you have just the Gaussian curvature of the curve, which is the image of the singular on the sphere, and this is just the arc length element on the sphere. So this is Gaussian curvature of this singular set, but on the sphere. Okay. And the next one, we have also 2 formulas you can obtain by the result of Saju, Mehara, Yamada, but in fact it's a Queen theorem. So if you, under the same assumption, so we have a surface oriented, closed, and we have immersion, and that satisfies the generic properties 1 and 2, that guarantees the only singularities are fold and cusp. Then, if you take 1 over p of the Gaussian curvature times the areas, also total Gaussian curvature, then this is sum from I equal to 1 to 2, and here this is Euler characteristic of mi plus and mi minus. So what this means? Mi plus, this is the set that Gaussian curvature is greater. This is here you obtain or normal curvature or minus normal curvature, depending which I is 1 or 2, and minus is the other part, okay? And you have this Euler characteristic, and now you have the sum of positive and negative cusp point. If you have a cusp point, yes, okay, here is the image. So how you detect which is positive, which is negative? You just look at this part of your surface that locally around this cusp point, this is an injection, yes? And if it preserves orientation, this is positive cusp. It's maps here, yes, not inside the cusp. And if it does not preserve the orientation, it's negative. Yes, it's negative cusp. Okay. So we have this formula. This formula also, if you have instead of immersion, you have embedding. So this formula is simplified, yes, because when the integral total Gaussian curvature is by a classical Gauss-Bonnet theorem is the Euler characteristic of M. And when you have this, because the normal curvature, the total normal curvature is 0. Yes, if you take the integral, and then you get this simplified formulas. Okay. Okay, and that's and multi obrigado. Thank you very much.
Thank you. Thank you very much. Are there questions?
Thank you, Wojtek. Very nice. So, so you don't capture the double points in your projection, right?
I don't understand.
So your Gauss map may have double points.
May have double point.
So,
yes.
but you don't capture them, so they don't appear in your...
In the formulas, they do not appear.
Yeah.
Yes, but they don't do, no, they do not appear, double points. Yes.
So other question, maybe I missed it, but did you characterize the fold and cusps in terms of the...
Yeah,
the
I
geometry?
should say so. Yes, I should say so. That's a good question. Because I should say one thing, which if you look at this, okay, this Pfaffian system, how we characterize, this is no, so this condition is understandable because this is a singular set, yes? But if you take this Pfaffian system, yes, so I take all the vectors tangent to the manifold which satisfies both equations. This is one form. So, but these forms that not depend on the choice. The forms depend on the choice of the orthonormal frame, Darboux frame. But if you take the kernel of the Pfaffian system, it does not depend on the choice of the orthonormal of this Darboux frame. So they are independent. So they are this invariant. This line it has geometric meaning because it does not depend of the choice of the orthonormal frame. So if you have this and it does not depend, then you can set what it means that is transversal and what it means it's one tangent. Yes, so this is that we cannot interpret with the known invariants because it's a third order invariant. Because yes, that this is something. Yeah, we try to find, especially Federico from the beginning know that we cannot find, but I tried because I'm a new person in this. But then we can prove it that it's independent of the choice of the Darboux frame. So no matter frame you choose, you obtain the same. So this is the invariance. Yeah.
And are these the conditions, the generic conditions for the singularities of the components to
have this condition? Oh, sorry. This condition that the kernel of this Pfaffian system is transverse to this curve, yes, is condition for a fold. And if it's one tangent, yes, then it says cusp. One tangent, I mean it's one tangent, not two tangent. Yes, it's one tangent. It's tangent, but only one tangent.
Maybe you have said that, but what do you translate that to the immersion, to the geometry of the immersion in this case?
Because how I translate it, because I obtain this I should maybe say new invariant, because this line is a new invariant. Yes, this line is a new invariant. It appears at this point, yes, and it is translated in such a way that the kernel of the Pfaffian system does not depend on the choice of the orthonormal base. Yes, of this Darboux frame. No matter, you can always choose, but always you obtain the same object, geometrical object. Yes, so this is a new object, and this is geometric. Yes.
Okay, thank you. Are there more questions? Oh, so we thank you again. Thank you very much.
Thank you.
It's a pleasure to introduce the next speaker, Thais Maria Dalbello. Thais has master degree and PhD at ICMC USP, and also a PhD by Aix-Marseille University French. Thais works in Department of Mathematics at UFSCar, São Carlos, Brazil. Her research involves topics related to topology, singularities, and the dynamical system. She will talk about Newton polyhedron and the Whitney X singularity for determinantal singularities.
Thank you, Ana Cláudia. So, good afternoon, everyone. First, I would like to say that it is a pleasure to meet all here in São Carlos after so complicated times. And we are all here thanks to the great work that the organizing committee has been doing. So I would like to thank the organizing committee for this very good work. And I also would like to thank them for the opportunity Today, I'm going to talk about determinantal singularities, Newton polyhedra, and Euler obstruction, which is a joint work with Luis Hartmann and Michael Varela. This presentation is divided in 4 topics. First, I'm going to do an introduction. After, I'm going to talk about determinantal variety and some of its properties. In the sequence, I'm going to present a definition of Newton polyhedra for matrices and talk about of some concepts related to it. And finally, I'm going to talk about the local Euler obstruction, and I'm going to present a formula to compute this invariant using Newton polyhedras. So, determinantal varieties has been widely studied by researchers in commutative algebra and in algebraic geometry. In singularity theory, there are countless articles dedicated to study the properties of these varieties. And one of the reasons why that makes this class of varieties so special is that they are a generalization of the concept of complete intersections variety. In the last 2 weeks, we had here in São Carlos the Simple School, and we had some very good courses. And one of them, it was this one, Singularities, and the algebraic methods. This course, it had 2 parts. In the first one, we studied complete intersection with isolated singularity. And in the second part, we studied determinantal singularities. So to those of you that would like to find the material and the videos of the classes, I invited you to go to the website of the Simple School. There you'll find the material. So one interesting question that arises is what concepts and properties of complete intersections we can also consider for determinantal singularities. For instance, there is many work dedicated to study the complete intersections, the properties of the complete intersections using Newton polyhedra. For instance, there are the Newton polyhedras are used for many authors to describe the topology of the Milnor function, of the Milnor fiber of a function defined in a complete intersection. In this work, Sterov used resultantal varieties and the torque varieties to describe to give a formula for the Euler characteristic of the Milnor fiber of a function defined in a determinantal variety using Newton polyhedra. For this, he introduced a kind of non-degenerated condition. And we use this concept defined by Sterov and the equivalence of matrices to present a formula for the Euler obstruction of the isolated determinantal variety. So we denote by MNK the set of complex matrices of size n times k. And we denote by MNKS the set of matrices with rank less than S. This set, MNK, is a reducible variety of the set of matrices MNK. And the codimension of this variety is given by this product. And it is called a generic determinantal variety. The singular set of this variety is exactly this set here, M and K S minus 1. And if we consider this set here, this difference of sets, what we have is a submanifold of the set of matrix. So if we consider this, all this set for all t between 1 and s, then what we have is a decomposition of the generic determinantal variety into a smooth variety, into submanifolds of MNK. And this collection of sets satisfies a good property, satisfies a good regularity property. And in fact, this collection is a witness stratification of this variety. Okay, so if we consider, for instance, this set of matrix, then we can consider, for instance, this generic determinantal variety. And here, the singular set of this variety is in fact, just the zero matrix. Okay? Then, in this case, we consider here this collection of submanifolds. What we have in this example is just two sets. That we call strata. Then this form a witness stratification of this variety in this case. Now, let A be a holomorphic map germ defined by this way, where all the entries of this matrix is a holomorphic function. And we denote this set by XAS. And we say that XAS is a determinantal variety of type NKS if its dimension is equal to this number, which means that its codimension is given by this product. In fact, XAS is the zero set of the ideal generated by all minors of size S of the matrix defined by A. When S is equal to 1 and XAS is a determinantal variety, then XAS is a complete intersection. And conversely, if we have a complete intersection, then it is a determinantal variety. In this work, we will consider some, I will present some results for isolated determinantal singularities. And this concept of isolated determinantal singularity is given in this way. Let XAS be a determinantal variety satisfying one of these conditions. Then XAS is said to be an isolated determinantal singularity that we just denote by IDS if XAS is smooth at X and the rank of this matrix is equal S minus 1 for all X that is different of 0. Okay. For instance, if you consider this map here, and this matrix given by this map, then in this case, we have 3 2x2 minors that are these binomials here. And in this case, XA2 has dimension 2 in C4, then XA2 is a determinantal variety in C4, and it has, in fact, it is an isolated determinantal singularity. The isolated determinantal singularity has some special properties. For instance, they has a special smoothing, which is called a determinantal smoothing, which was studied by Pereira and Ruas for codimension 2 and by Nunes Ballesteros, Horácio Okamoto, and Tomazello. And to describe it, we can describe it as follows. If we consider XAS and IDS, then the authors, they proved that there exists a Zarinsky open set W, wherefore all constant matrix B in this set, this map AB, given by this sum, provides a smoothing, a determinantal smoothing for this variety. And here, it doesn't depend of the constant matrix B. But the determinantal smoothing, it depends on the analytical structure of the variety, as we saw in the lectures, in the classes, in the last week, which Professor Gaffney called a landscape. Using this smoothing, the authors defined the vanishing Euler characteristic of an isolated determinantal singularity by using the information of the Euler characteristic of the determinantal smoothing. The vanishing Euler characteristic has some important properties. For instance, it has a kind of Legruel type formula, which relates these vanishing Eulers with the top polar multiplicity of the determinantal variety. Okay. Now, although it depends, the smoothing, it depends of the analytical structure of the variety, the smoothing, it doesn't depend of equivalence of matrices. By equivalence, I mean this equivalence here. We say that two matrices are equivalent if there exist P and Q invertible matrix such that we can write A tilde in using by this product here, which are basically row and column operations. If two germs of matrices are equivalent, then the determinantal varieties are equal. This equivalence does not change in variants such as the multiplicity and the local Euler obstruction, as we will see after in this presentation, and it doesn't change also the vanishing Euler characteristic. For instance, if we consider this matrix of our previous example, and if we take B, this constant matrix, I'm sorry. In this case, if we consider P and Q, two invertible matrix, then we have that this matrix A tilde, given by this product, which is in fact this matrix, and we have that B tilde is this matrix here. Then, in this case, the map AB that we saw in the previous slides gives a determinantal smoothing of this determinantal variety, and also this map gives a determinantal smooth of this variety. And the determinantal smooth that they provide is the same. They are equal. Okay, now I'm going to talk about Newton polyhedra. We denote this monomial here in this way. Then let f be a polynomial function denoted by this way. This set here that we call support of f is the set of all degrees A which appear here in the expression of f. And for each one of these degree, we can do this sum, this Minkowski sum, and the Newton polyhedron of f is the convex hull of this union. We say that a coefficient is a leading coefficient of f if A, the degree associated to this coefficient, is contained in a bounded face of the Newton polyhedron. And we say that the leading coefficient of a matrix are the union of all leading coefficients of all entries of A. For instance, if we consider this binomial, then the support of this binomial is a set with these 2 points, the point 30 and the point 02. And doing the Minkowski sum for this point, we have this set. For the other point, we have the set. And the convex hull of the union of this set is given by this picture. And this is the Newton polyhedra of this function. Polyhedron, sorry. And let us observe that these 2 points, they are in a bounded phase of the polyhedron. So these 2 points represent leading coefficients of this binomial. Now, we denote by FL the lowest order non-zero L quasi-homogeneous component of F, where L is a collection of positive weights associated to the variables. Then, instead of, presented this definition. Let A be a germ of a matrix with polynomial entries. The leading coefficients of A are said to be in general position if for every collection L of positive H's and for every subset I in the set of possible rows, the set of points in the algebraic torus such that this matrix is degenerate has the maximal possible codimension, which is this number here. Using this concept, instead of present this result, let delta J be the Newton polyhedron of each entry of the polynomial matrix A, and let us denote this set by XAN, which means here it is the set of the pre-image of the matrix that don't has maximal rank. If the complement of the delta J in Rn is bounded for all columns of this matrix, and if the leading coefficients of A are in general position, then A defines a determinantal singularity whose the multiplicity is given by this expression, where L denotes the standard m-dimensional simplex in Rm. This multiplicity, which appears here, is the same multiplicity that Alexandre Fernandes defined yesterday in his talks. And here, what we have, which appears, is all the Newton polyhedrons of the columns of this matrix. And MV denotes the mixed volumes between these polyhedrons. Okay, now let us consider this example, our previous example, and let us observe that none of the entries of this matrix has a Newton polyhedron with bounded complement. Okay, and moreover, this matrix is it is not in general position, because, for instance, if we consider I this subset of the set of possible lines, then what we need to check is this line here. So we need to look for this equation, okay? So the set of points that satisfies this equation is this set. And the intersection of this set with the algebraic torus is empty. So it doesn't has the expected codimension, which is 1 in this case. Because of that, this matrix is not in general position. However, if we repeat the rows and column operation that we did in the previous example, then we have this matrix. This matrix A tilde, it is in general position, and also we can observe here that all entries of this matrix has a bounded Newton polyhedra. I mean, has the complement of the Newton polyhedron bounded. Moreover, all the Newton polyhedrons of the all entries are the same. They are equal. Okay. So, what are the effects that the equivalence of matrix? What are the effects of the equivalence of matrix on the definition of a general position? As we saw in the previous example, there are some germs of matrices whose the leading coefficients may be brought into the general position, as this one that we haven't seen. And there are also germs which may not. For instance, I'm sorry. If we consider this matrix, okay, which is a simple determinantal singularity, which appears in the classification of Anne, Frobes-Gruger, and Neumann. Then X A2 is a curve. And if we consider L this H, then this restriction is this matrix here. Okay, and this matrix doesn't satisfy the condition necessary to this, so this matrix can be in general position. And moreover, for all equivalent matrix A tilde, that for all equivalent matrix A tilde, what we have, in fact, is that equality. So it doesn't matter the operation that we do in this case, that this matrix is not in general position. And what about the effects of the equivalence of matrices on the Newton polyhedron? As we saw in the previous example, in this one, the Newton polyhedron of each entry of this matrix, it changed. And it changed in a good way, because here all the entries have a bounded Newton polyhedron. So what we would like is a definition of Newton polyhedra that don't depend of the equivalence of matrices. So we define the Newton polyhedron of a matrix in this way. If A is a germ of a matrix, the support of A is the union of all the supports of the entries of this matrix. And the Newton polyhedron of the support of A is denoted by delta A. For instance, in this case, in this example, the Newton polyhedron, the support here of the matrix A is these 3 points, which appears here. So, doing the Minkowski sum and consider the convex rule, we have that this is the Newton polyhedron of this matrix. Given a germ of a matrix A, there always exists a germ A tilde equivalent to A, such that the Newton polyhedron of all entries of A tilde are equal to the Newton polyhedron of the matrix A. And let A be a germ of a matrix with polynomial entries and the Newton polyhedron, delta A. We say that A tilde is delta A equivalent to A if A tilde is equivalent to A, and the Newton polyhedron of each entry of A tilde is equal to the Newton polyhedron of the matrix A. Let A be a germ of a matrix with polynomial entries. The leading coefficients of A are said to be in weak general position if there exists a germ A tilde, delta A equivalent to A, such that the leading coefficients of A tilde are in general position. Using these concepts and the result proved by Sterov, we can present this result. Let A be a germ of a matrix with polynomial entries whose Newton polyhedron, delta A, has bounded complement in Rm. If the leading coefficients of A are in weak general position, then A defines a germ of a determinantal singularity whose the multiplicity is given by this expression. Let us observe that here, now, what we have is the same Newton polyhedron. It appears more than once, but it's the same Newton polyhedron. So, for instance, before, let me do one remark. The mixed volume of polyhedrons has this property. If we have the same Newton polyhedron here, don't matter how much times it appears, this mixed volume is equal the volume of the polyhedron, the Euclidean volume. Then, if we, under the same conditions of the previous theorem, if delta A tilde is equal to L, to the standard simplex in Rn, then using this equality, the previous formula is, in this case, this formula, which is just a binomial coefficient. So, for example, in this case, the multiplicity of this determinantal surface is equal to 3. Okay, now I am going to talk about the Euler obstruction. The Euler obstruction was defined by Macpherson as one of his main ingredients to prove the conjecture of the line and Grothendieck that concern about Euler characteristic class of singularity variety. And sometime after, Bracelet and Schwarz presented an equivalent formula using vector fields. An equivalent definition using vector fields. So this definition of Bracelet and Schwarz brings the Euler obstruction to the class of the indices of vector fields. The definition, it is in fact very difficult to compute the Euler obstruction using its definition. So many authors has presented formulas to make this computation easier. For instance, Bracelet, Le and Seade presented this beautiful formula. So let X be an equidimensional complex analytic singularity with a Whitney stratification V, and let L be a generic linear form with respect to X. Then the Euler obstruction of X at 0 is given by this expression, by this sum, where here this denotes the Euler characteristic of the Milnor fiber of L restricted to its stratum. And here what we have is the Euler obstruction of X in a point of the stratum V. It's important to say that the Euler obstruction it is an invariant in a stratum of a Whitney stratification. So here, if we choose two different points of this stratum, this doesn't change, okay? So as we saw in the beginning of the presentation, the generic determinantal variety has a stratification, a Whitney stratification given by this set. And using this stratification and the previous formula, Gaffney, Grullier Jr., and Ruas presented, they proved this theorem. They proved that the Euler obstruction of this generical determinantal variety is given by this formula, this beautiful formula, because it is just a binomial coefficient. Okay, now one more definition, which was presented by Sterov. The leading coefficients of A are said to be in strong general position if for every collection L of positive H's, the polynomial matrix given by this restriction defines a non-singular determinantal set in the algebraic torus. In this case, the leading coefficients of a function f are said to be in general position with respect to A if for every collection L of positive H's, the restriction of the derivative of f to the determinantal set defined by this matrix has no zeros in the algebraic torus, which means that FL has no critical points in this determinantal set. This is a kind of generalization of the concept of a non-degenerated complete intersection. Now, using this definition and the results of Sterov, we represent this result. So let delta A be the Newton polyhedron of a holomorphic matrix, and suppose that the complement of the Newton polyhedron of this Newton polyhedron is bounded, and let us assume this condition. If the leading coefficients of A are in strong general position, then the determinantal singularity, xan, has isolated singularity. If the Newton polyhedron of the function f intersects all coordinated x, which means that this Newton polyhedron has a complemented bounded, and if the leading coefficients of the derivative of f are in general position with respect to A, then the Euler characteristic of the Milnor fiber of f restricted to the determinantal variety is given by this expression. Well, here it is a big expression, right? But here, for instance, what we have are products and sum of binomial coefficients. And here, what we have are mixed volumes, okay? Now, as we can see in the first part of this theorem, this variety has isolated singularity at the origin. So, in this case, one Whitney stratification of this variety has just two strata. One Whitney stratification is the origin, and the variety minus the origin. So, using this stratification and the formula for the Euler obstruction presented by Bracelet, Le, and Sead, and using this equality, we have this corollary. Then, if delta A satisfies the hypothesis of the previous theorem, and if the generic linear form L has a bounded Newton polyhedron, and the leading coefficients of L are in general position with respect to A, then the Euler obstruction of the determinantal variety xan is given by this expression. And for instance, when A satisfies the condition for the previous corollary, and delta A tilde is the standard simplex in Rm, then the Euler obstruction is given by products and sum of binomial coefficients. For instance, if we consider this matrix, the Euler obstruction, in this case, is given by this expression, and doing some computations, this is equal to -1. Another example, if we consider this matrix, also presented by Anifrubis, Gruger, and Neumann, and then after some computations, a lot of computations, the Euler obstruction in this case is 2. This number, this Euler obstruction, was also computed by Nancy Chachapoyas in her work. So, look that here we are in C6. So the Newton polyhedron are in R6. Then it's not easy to do this kind of computations. However, one of the authors, Maicon Varela, using the mathematical software OSCAR that we also studied in the Simple School. He presented a routine, a program, I don't know how to say, to compute the Euler obstruction of determinantal varieties using the informations of the Newton polar header. Just to finish, using these informations, we can also compute some generalizations of the Euler obstruction. For instance, the local Euler obstruction of a function that was defined by Bracelet, Massey, Paramis-Varan, and Seade, and the Bracelet number, which was defined by Dutertre and Grulha Jr. So here I put some of the reference that we used. It's important to say that the work of Sterov is very important for us. We use it a lot. Here others reference, and of course that there are more, but I didn't put here. And this is it. Thank you for your attention, and happy birthday, Professor Saek.
Are there any questions?
If I want to look at matrices that only have linear entries, for example, I fix a Q and I fix the size of my matrix. Can you write down examples of matrices of this type, in which all the coefficients are, I think, let's see, you call them in good position?
Yes.
Yeah.
So, yes, we can. For instance, here we have this matrix, okay? And this matrix, it is not in general position, but it is in strong general position, and all the entries here are linear, and we can apply this result. And although it is not in general position, there is equivalent matrix A tilde here. I'm sorry. Here. Oops. I'm sorry. Here. Oops. It is not in general position. However, this one it is, and all the entries are linear, and we can also compute the multiplicity.
What I'm wondering is, do you have a technique? So if I gave you a 10 by 11 matrix, you could immediately write down one where the entries were linear forms, and it was going to be in general position.
Oh, it is an interesting question. I don't know the answer. Okay. Thank you. Thank you.
Yes. Thank you. So thanks for your talk. It was nice. I have a question, but you did not mention the work of two Japanese.
Yeah.
So I am still in Japan.
Maybe.
And yeah, is it a relation between in this work of the two Japanese that I think you know,
Yes.
and the Esterov work?
Yes. you say of Matsui and Takeuchi? Yeah,
exactly.
Yes,
Exactly.
it is a very good question, and there is relation because to present the results instead of, in fact, what he did is to work with resultantal varieties, and he did a resolution of the resultantal varieties, in fact, a toric resolution, and he also proved that the determinantal varieties are resultantal varieties. And the work of Matsui and Takeuchi are exactly for toric varieties. So is there a relation? Okay.
You have one formula for the multiplicity, I think. Can
Yes.
we see that formula again?
This.
I think it was in the end a binomial coefficient.
I think it's here.
And it does not seem to depend on the matrix, right?
No.
I think it was not this formula, but
it depends because here we have these polyhedrons are the complement of the Newton polyhedron of the matrix. So, in fact, it depends.
yes. But didn't you have another formula?
I see. Maybe this one?
Yes. Can you say some words why the matrix A does not play a role here?
Yes. In fact, it does, but it is hidden because here we have this condition that the Newton polyhedron, the complement of the Newton polyhedron of the matrix A is the standard simplexity, which means that if we consider, for instance, a matrix, like that, I don't know, just an example. And if this matrix provides a determinantal variety, and if the degrees of F and J are bigger than 1, then what will appear in the Newton polyhedron of this matrix comes from these 4 entries here.
Yeah, okay.
For variables.
And then you substitute this in the other formula we looked before, right?
Mm-hmm.
And something similar seems to happen in the end where you have this other example from C6 to the space of matrices and U to the K, and the K does not appear on the other side, I think.
Yes.
Is it the same effect?
Here, let me see. This one, right?
Yeah.
Here, no, I don't know, sorry, because here, in fact, K can be bigger than 1, and we don't have the variable U appear in other place. I don't know. I think that in this case is what happens is that some of the volumes which appear here, one can cancel each other, and in the end it doesn't change. I don't know.
Okay, maybe we can look this up. But
Yeah.
in general, there's the question. I mean, we've seen in the courses that this notion of EIDS has become central in this whole theory. And from your talk, it's not a priori clear how the non-degeneracy that you require in your theorems, how this is related to being an EIDS. Do you think there can be more structural connection established?
Yeah, I think, in fact, it is an interesting question. I was talking with Michael this week about that because, for instance, here, if we look to this condition in the work, for instance, of Eblin and Guzenzade and in the other works, if this map is transverse to the rank stratification, then with the transversality and with this condition, automatically the singularity is isolated. However, here, we don't ask that A is transversal to the rank stratification. So we are trying to understand this better yet, but maybe these general positions are related to some transversality conditions.
Yeah, I think what Terry mentioned before is would be a good testing ground to start with linear EIDS and really look into how Newton non-degeneracy in your sense relates to being an EIDS.
Yes. You are right.
Okay, thanks.
Thank you.
Thank you, Thais. Very nice talk. So your formulas hold for the case that the determinant of singularity has isolated singularity, right?
Yes. This for the Euler obstruction, yes. But for the multiplicity, no.
Okay.
Yeah.
Because for the Euler obstruction, then when you have the non-degeneracy condition on the Newton polyhedra, maybe you are already saying that this principal part of your matrix is an EIDS. I mean, is an IDS, right? Because it's sufficient to know it has isolated singularity to know it's an IDS,
I see.
right? So, and another thing, it's I suppose that in this case, you always can assume, yes, at least in the case that the entries of the matrix are linear, then you always can assume the Newton polyhedra is non-degenerate. I mean, you can always find the one normal form which Newton non-degenerate. Do you think so? If you have isolated singularity and the entries are linear, then I think we can always apply your formula, right?
Yes. Yes, maybe because after some rows and color, yes, I think so. Okay. Because after some rows and color operation, we can proceed like in this example, for instance. Yes, I think so. I'm sorry here, because what may happen is that the matrix is not in general position, but after some rows and color operation, yes. And this doesn't change the invariance.
Yeah, it doesn't change the invariant. Yeah. So, but in general case, for any EIDS, then it's more complicated than.
Yeah.
Okay.
More questions? Let's take the speaker again.